So this problem says a marble rolls off a tabletop 1 meter high and it hits the floor at a point 3 meters away from the table's edge in the horizontal direction. How long is the marble in the air? What is the speed of the marble when it leaves the table's edge? What is its speed when it hits the floor? Okay, so these are two-dimensional problems, and one of the first things you want to do is the following. So you want to set up your coordinate system. And I won't draw the details all the time, so let's say this is XY axis. And so a marble rolls off a tabletop. So when it's rolling off, you see its velocity is horizontal. Okay, and what you want to do is write it in component form, all of these guys. When the marble has rolled off the top, during this flight, what is the force acting on the marble? Gravity is the only force acting on it. And so the acceleration during flight is 0I minus gj. And g is 9.8 meters per second squared. Okay, so that's the setup. And now what is it that you want? How long is the marble in air? So the flight time is what you want. What is the speed of the marble when it leaves the table's edge? Okay, so, and they tell you that it falls 3 meters away. Okay, now you guys know that the faster the marble is launched from the tabletop, the further it falls. So this information is going to give you the speed. Okay, and of course this is related to the speed and the time of flight. The longer the marble is in air, okay, the smaller the speed needs to be for this given distance. Okay, so from this information we need to back up, we need to surmise the initial speed. Okay, what is the speed of the marble when it leaves the edge, and what is the speed when it hits the floor? What is this asking for? See, there's the trajectory, the velocity is tangent to the trajectory. Okay, so actually let me, so there's the trajectory and the velocity is tangent to the trajectory. That's the final velocity, and speed is the magnitude of that velocity. Okay, so I'll do this problem in detail, and there are similar problems, but you get the idea. Okay, okay, so again the setup is you want to write the initial velocities and acceleration in component form. All right. So what will part A, how long is the marble in air? So we'll do that part first. Okay, so for the time of flight, what we'll do is we'll use, of course you need an equation with time involved. Okay, so here's one equation. We'll use this because we know the final location, y location of the marble. We know the initial y location of the marble, and we know everything else. Okay, what is the final y location? 0 meters, 1 meter. This was 0. Initial y component of the velocity was 0 because the marble comes off horizontally from the tabletop. Okay, so that was 0. And the y component of the acceleration is minus g. Okay, so actually I won't write, I'll write this as y naught. Okay, so here's a general expression. If you drop an object from a height y naught, the time of flight is 2y naught divided by g, square root of that. Okay. Of course, if you throw it with the velocity, y component of the velocity, the time would be different. If you drop it from a height y naught, that would be the time of flight. That, okay. So 2 times 1 meters divided by 9.8 meters per second squared. And again, the meters cancels, the second square there, square root of that will be a second. Okay, so okay, so that was the time of flight. So what is the speed of the marble when it leaves the edge? Now let's look at the x component of the motion. X minus x naught equal to v naught x t plus 1 half ax t squared. The x component of the acceleration is 0. Okay. We'll say this is the origin. Okay, x naught was 0. So x naught is 0. X is 3 meters. The final location is 3 meters. So x equal to, and the x component of the velocity is just the initial speed. Okay. So v naught, the initial speed, the launch speed, is x divided by t, which is 3 meters, divided by 0.545 seconds. Just 6 meters, 6.6 meters per second. All right, now let's do the final velocity. Okay, so what we are calculating is the final velocity. Okay, Vx is v naught x plus ax times t. Ax is 0, so this would be v naught x, which was v naught. So the final x component of the velocity is just the initial speed. Vy, you guys following this? Vy is v naught y plus ay t. V naught, this was 0. Initial y component of the velocity was 0. Ay was minus gt. Okay, so minus 9.8 meters. And you can see that there's the x component of the velocity and there's the y component of the velocity, and the y component of the velocity is negative. Okay, so okay, so the velocity at this location, the final velocity is 6.64 I minus 4.41 J meters per second. So there's, okay, those are the units. That's the final velocity. And of course, what they want is the speed, which is, they want the magnitude of that velocity. And so the speed is 6.64 squared plus minus 4.41 squared. Okay. So it hits the ground at that. Okay, and let's find the angle as well. Okay. So theta is tan inverse, so V was 6.64 I. Okay, so the vector is in the fourth quadrant, okay? And if you measure the angle clockwise with respect to the x-axis, that's a negative angle, okay? So tan inverse of Vy over Vx minus 33.59 degrees, okay? And that was the correct angle, okay? So this is negative 33.6 degrees, okay? And if you wanted a positive angle, this would also be equal to plus 360 degrees, which is 326.4 degrees. Okay, so whenever you see those two-dimensional problems, the first thing you want to do is set up your coordinate system, write down your initial velocity, write down your acceleration before you do anything, okay? And then the y motion will give you the time of flight, and the x motion will be related to the initial velocity, okay? And this makes sense. The faster you shoot it, the further it'll fall, okay? The higher you shoot it from, the longer it's in flight and the further it'll fall, okay? So the distance it falls is related to how fast you shoot it and how long it's in flight, okay? So let's do one more problem like this, okay? So this says an airplane flying horizontally with a speed of 500 kilometers per hour at a height of 800 meters. 800 meters, when you've been on the beach, you've seen those Embry-Riddle planes flying. They're flying at about 800 meters high, okay? So, all right, so you're flying at that height and you drop a crate of supplies. So when you drop this crate, what is the velocity of the crate? It's whatever the velocity of the plane is, okay? So the initial velocity is 500 kilometers per hour I plus 0j. Okay. And you want to learn to do this quickly. A kilometer is 1,000 meters, an hour is 3,600 seconds. So essentially, all you're doing is, dividing this number by 3.6. Okay. Okay, so the initial speed is 138.9 meters per second. All right, so now let's set up the problem. And that's in meters per second. acceleration is 0I minus gj, and the initial height is 800 meters, and this thing falls like that on a parabolic trajectory. Okay, what is it that we want to find? Drops a crate of supplies. If the parachute fails to open. So what are they saying? If the parachute fails to open, that means this object is only traveling under the influence of gravity. If the parachute had opened, then you would have a force that was comparable to gravity, and then everything goes out the window. Okay. How far in front of the release point does the crate? So they want you to calculate the horizontal distance. Okay. And again, the horizontal distance depends on the speed, launch speed, and the time of flight. We already have the launch speed, so we want the time of flight. And the time of flight is obtained by looking at the y component of the motion. Okay? So let's get the time of flight first. Okay, so again, our axis is there. This is y naught, this is y is 0. So minus y naught. V naught y was 0. V naught y is 0. Okay. And just like last time, okay, if you do not have a y component of the velocity, if the y component of the velocity is 0, that means it's the same as like you're dropping it from rest. And if you drop from a height of y naught, the time of flight is that 2y naught divided by g. Okay, if you have an initial velocity toward the ground, then the time of flight will be less. If you have an initial velocity upward, the time of flight will be greater. Okay. So this is how long the package was in air. 2 into 800 meters divided by 9.8 meters per second squared. Okay, so that's a long time, 12.8 seconds. Yep. Now we want to calculate the horizontal distance. Okay, so the x component of the acceleration is 0. You see the x component of the acceleration is 0. We'll say, oops. This is 0. All right, so the final x location is initial x component of the velocity we found is 138.9 meters per second. And the time of flight was 12.8 seconds. Okay, so 1.8 kilometers, a little over a mile away. All right, so this is assuming there's no drag and stuff like that. So back in the days, when you drop a bomb and you want to hit a target, this is the kind of calculations you would do. Did you hit your target every time? No, you would miss. So how do you improve that? Was that? So now, what you do is you attach a rocket to your bombs and laser guide them. And now you can hit one building between two buildings, you know. You can make your bomb go through a window. Yep. All right. Are you guys okay with me finishing the problems at the 20 more minutes of problems? So I'll just pick and choose. Or you want me to do all problems? Picking, okay. So this is slightly harder, and okay, this is sort of similar to what we did, but you also have recordings, so okay. We'll do this problem. Okay, again, this is a parabolic trajectory. Okay, so projectile, soon as they say the word projectile, what that means is it's traveling only under the influence of gravity. Okay, so it's shot at a hill, the base of which is 300 meters away. The projectile is shot at 60 degrees above the horizontal with an initial speed of 75 meters per second. The hill can be approximated by a plane sloped at 20 degrees to the horizontal. So there's the, on this line, y and x are, so that's the equation of this line. Okay, this is in the slope intercept form. There's the slope and there's the intercept. The y-intercept is 109 meters below that point. Okay. Where on the hill does the projectile land? So they want you to find the final xy location. Okay. So that's what they want you to find. All right, again, this is a projectile problem. So what is it that we want to set up? We want to set up our initial velocity and final and the acceleration. Okay, and again, here's the x and y coordinates. So v naught initial velocity is 75 cosine 60 I plus 75 sine 60 j. Okay, so now we have set up the problem. Okay, the y component of the motion always gives you the time of flight. Okay, so the equation of the straight, what is the hill does the projectile line? Okay, so the x motion x component of the acceleration is 0. It starts off at 0. There's the final location. V naught x is 37.5 t. We want this fella. Okay. Y minus y naught equal to v naught y t plus 1/2 AY T squared. This is 0. So Y is V naught Y is there. 65T plus 1/2 negative 9.8 T squared. We want this, and we don't know T. All right, so, and we've run out of all directions of motion, X and Y, direction of motion. So it seems like we have 3 unknowns, X, Y, and T in this problem, and we had 2 equations. 2 equations given by the X and Y direction. Yeah. We have a problem. Are we missing anything?
The y equals tangent 20.
Very good. So the landing spot, at the landing spot, these 2 guys are related. And they're related by this equation, as our friend noticed. Okay? Okay, so we are going to use that. Okay? And that's a third equation. And so, okay, so what we'll do is we'll put this there and this there to get solve for T. Okay, so y is tan 20x minus 109, except y in terms of T is this 65 T minus 4.9 T square equal to tan 20. X is 37.5 T minus 109. And now we can solve for T. Once you have T, you can get Y and X. Okay? And I'll let you guys do that. Okay? All right, I'll set up this problem. So what is the acceleration of Venus towards the sun? So here's the sun. Here's Venus. And most of the planets have almost circular orbits. Okay. The acceleration is the centripetal acceleration. And what you can do is you can look up the orbital speed. Okay, so let's do this for Earth. Okay, so for Earth, the velocity is 30 kilometers per second. I remember that. So R is 92 million miles. So okay, and you can calculate the acceleration. So, and what is providing this acceleration? It's the gravitational force that's providing that centripetal force. And so, you know, the moon's orbit around the Earth was known, and Newton used when he discovered his law of gravity, when he came up with the law of gravity. That's one of the first checks he did. All right, so you guys can calculate that. Okay. Right, so I want to do these two problems. So let's do this. Okay, so this is a relative velocity problem. Do you want to do a boat moving in a river or a plane flying in the wind? It's the same problem. Uh, huh? The boat. Okay. So it says a river is moving east at 4 meters per second. So that's the velocity of the water. So, okay, so the velocity of the water with respect to ground is 4 meters. Again, it's in that direction. And so velocity of the water with respect to ground is 4I plus 0j. And everything is in meters per second. Okay. A river is moving east. A boat starts from the dock heading 30 degrees north of west at 7 meters per second. Okay, so 30 degrees north of west, 7 meters per second. Okay, so there is, and that's the velocity of the boat with respect to the water. Okay, so velocity of the boat with respect to water is so negative 7 cosine 30I plus 7 sine 30j. Okay. What is the velocity of the boat with respect to Earth? So what we want is the velocity of boat with respect to the ground is velocity of boat with respect to water plus the velocity of water with respect to the ground. So again, remember, the way to remember this is you insert a letter in between. So velocity of boat with respect to water plus velocity of water with respect to ground. Okay? So this is the velocity of the boat with respect to ground. This vector plus that vector. Okay? So let's just add the two vectors. So the velocity of the boat with respect to ground velocity of boat with respect to water is that. So you see the velocity of boat with respect to the ground is somewhere in that direction. Okay? It's this angle is less than 45 degrees since the y component is larger than the x component. Okay? So you start off on this end, you're not reaching that end, you're reaching somewhere there. Okay? how long does it take the boat to cross the river? So to cross the river, you have to cover this distance along the y-axis. So all we'll do is look at the y motion. Okay. So to cross that river, okay, and the river is 1,800 meters wide. Okay. So let's look at the y motion. There's y naught. Okay. V naught y. Of course, it's not accelerating. Okay, the boat is moving at constant velocity. We'll take this to be 0, 1,800 meters, 3.5. The y component of the velocity is that. So 8.5 minutes. Yep. Mm-hmm. I'm sorry? Oh, that's the width of the river. If the river is 1,800 meters. Okay, so this kind of stuff is you have to do all the time. Pilots have to do all the time. They're always dealing with winds. Winds, so planes fly at 600, 700 kilometers a second, passenger planes, and wind velocity, they have to deal with wind velocities of 10%, 15%. Okay. And well, of course, if you fly on jet streams, jet streams can be up to 200 kilometers a second. So that's 30% of your velocity. Okay. Okay. A geosynchronous satellite orbits Earth at a distance of 42,250 kilometers and has a period of 1 day. What is the centripetal acceleration of the satellite? What is a geosynchronous satellite? Anybody know what that is?
Specific point.
So, a geosynchronous satellite it'll be in the same spot in the sky. Okay, and this is only possible. Okay, so, oops. So here's the Earth. It's rotating that way. Okay, so geosynchronous satellites, they have to be above the equator. Okay, right above the equator. And this distance, this radius is 42,000 kilometers. Okay, and of course, they have to take 24 hours to go around once. The Earth is spinning 24 around. Okay, now at that distance, no matter what the orientation of this orbit, this will also take 24 hours, except that won't remain at the same spot. Okay, and you could go backwards, you'd still take 24 hours, and of course you won't be on the same spot. Okay, now this guy is very useful because you can bounce TV signals off, and it's very good for communication. You can't do telephone conversations because I believe the signal takes about 2 seconds to come back. Okay. For TV, it's no big deal, but for telephone conversations, it's not good. Okay. So it turns out that this is the most expensive parking spot for humans. Okay. So countries are allocated these parking spots. There you go. Okay. And back in the old days, it used to be 1 degree apart, but now they park them half a degree apart. So there's 720 parking slots. And of course, if you talk in different bands, you can park satellites into them. Okay? So Falcon Heavy can launch a geosynchronous satellite. Okay? Yeah, I don't think Falcon 9 can do it. Yeah. All right. So a geosynchronous satellite, orbits Earth at a distance of 42,000 kilometers. Okay. So it's 7 times the Earth radii. Okay, so that's and a period of 1 day. What is the centripetal acceleration? The centripetal acceleration is v squared by r. V is 2 pi r divided by t square divided by r. So there is the centripetal acceleration. Radius is 42,250 kilometers meters, and t is 1 day. 1 day is 24 hours, 3,600 seconds squared. Okay. And you can calculate that. Should work out around, I believe, 3 meters per second square or something like that. Okay. All right. So we will end this.